So tutoring can be online, like over Zoom or Teams, and so can academic success coaching. So if you just can't make it to the tutoring center or the learning lab, there's no time that works for you to be there, that's fine. They can work with you online if needed. So my team and I, we also use academic concern referrals just to proactively support you guys academically. So if a faculty member is kind of concerned that you might be falling behind, we might get in touch with you, just check in, see how things are going. Don't worry, you're not in trouble. We're just checking in, making sure that you're all right, and then connecting you with resources if needed. We're also offering student success workshops this year. This is what our promotional flyer looks like, so I'll just sum it up for you though. So there are going to be sessions throughout the semester covering time management, procrastination, original thinking, stress management, burnout, just things that, you know, we all kind of struggle with as students here from time to time. And then we also have the START office, which is here to help with enrollment, financial aid questions, and honestly, just general questions. So we're available in Price Hall all year long, Monday through Friday. We accept walk-ins, but if you prefer to set up a scheduled meeting, you're more than welcome to do so through our advising page. And I guess I'm the only START advisor who is not in Price Hall actually. So I'm moving to the library. I'm going to be helping manage the tutoring center this year. So if you prefer to work with someone who you've seen before, I'm fine with that. Just come see me in the library. We do all the same things. All right. And then lastly, we have the Emerging Eagle Leaders Program. So this is a program geared towards sophomores and juniors to help you guys gear up for career, learn those career readiness skills, that kind of thing. So it involves workshops that are hands-on and then also a mentoring program. So if you're interested, there's a QR code on the sheet. I'll maybe leave it with Dr. Everard. Otherwise, you can visit the Learning Labs website on the CSC page and learn more about that. You can join the program there. So, all right, that covers the 7 key resources. And as you get started this fall, I just want to encourage you guys to get in touch with these resources. Don't wait until it's maybe too late. That's not what we want. So if you want to set up tutoring or academic success coaching or just review the other resources that we have offered and that we covered today, just visit the Learning Labs webpage or swing by the library and we can get you connected. And then reminder for enrollment, financial aid, and general questions, you can always swing by Price and visit the START office and get those questions covered. So that's all I have for you today, but I would like to open up to any questions that you might have. David. All right. Thank you for your time.
Thank you.
Yeah, you bet. Okay.
Yeah, this is great. All right. Thank you very much.
Yeah, you bet. Have a good rest of your day.
You too.
Because I wrote these
Okay. All right, so before we can start to be into physics proper, we have to have an understanding of the mathematics that we're going to need. Trust me, it's not as intimidating as it sounds, and we'll practice it. It's not. Give me too many faces. I'm going to submit you for Eagle Leader. But everything that we're going to do in physics is going to be modeled with vectors. We have to understand what vectors are, how they apply. So in this first chapter we're starting with in the textbook, we're skipping over chapter 1, we're going to chapter 2. This chapter 1 is just kind of like this, hey, read all this stuff, here's some cool overview. We're going on to chapter 2. So, vectors. Now, we're going to be looking at two different quantities. We're going to be looking at scalars. We're going to be looking at vectors. Scalars are just a number. Vectors, we're going to use arrows to represent them, but they have both a magnitude, so the scalar part of it, and then they also have a direction that they're going to go. So one of the things you're going to have to get used to as we go along, and this semester it's more gentle, second semester it becomes much more important. You're also going to have to keep track of positive and negative directions. So we'll talk about that. Again, I have a standardized way that I do it. I use what most textbooks use. Now, here's the thing about positive and negative directions. You can really set your own positive and negative as long as your mathematics stays consistent. So if you're going to go off on your own and start setting your own positive and negative directions, you're going to be responsible for keeping track of your own consistency. But what I do in class, you're going to see that I'm going to mimic most textbooks. Whereas, like, if you have an XY axis, up is positive Y, and then to the right is positive X. And then the other way is negative X and negative Y. This is going to make a difference with your vectors. Now, here's a question. Now, in physics, it's like you can find the mean, and it's very true. It's like cow is a circle. But in physics, we're going to be drawing what's called free body diagrams. So let's say, I don't know, let's say we had some kind of object. Let's say maybe that's you, or like human is a rectangle. This is kind of how we do things. That is a sphere. But let's say we're asking about what gravity is doing to you, okay? Well, the first thing you would have, you're going to have the gravitational force pulling you down. Now, this is actually going to be a vector. Now, if you're standing on the floor, you're sitting on the chair, you're standing on the floor, you're not still falling through to the center of the earth. So you're being stopped. Now, this is Newton's third law. You're being stopped by an equal and opposite force. So as gravity pulls you down, the floor is pushing back with an equal and opposite force. Now, this is kind of like your first introduction to what's called a free body diagram. You're going to have to draw a lot of diagrams. Later on, drawing diagrams is going to help a lot because it helps you keep track of your vectors. Now, we'll get to it in time. This vector that's pushing back, that's keeping you from falling through to the center of the earth, that's called the normal force. Now, you notice how I put the little arrow on top of the end. That's how we denote vectors when we're writing it out. In the textbook, you'll see two different formats. You'll either see an arrow over the top of the letter, which denotes a vector, or you will see the letter in bold. Bold print also denotes a vector. Because here in a little bit, we'll talk about vector magnitude, and the magnitude in the textbook you'll usually see represented with just an unbolded letter. So if you have like a bold F, that's a force vector. An unbolded F is the magnitude of that force vector. Now, this vector pointing down, if you had to guess, you probably already know, so we'll want to ask someone else. I'll let you'll answer plenty of questions throughout the semester. I just want to see who else can get this. You have a weight and a mass. First off, did you know those were different? Okay. Did you really? Okay. Which one, your mass or your weight, which one is the scalar? Mass, because you're so many kilograms. Now, in this class, we're going to be using the SI system, so kilograms, meters, seconds. I'm not going to make you translate units from like English units into metric, because you only really need to do that if you're going into engineering. So we're just going to avoid that. But your mass, however many kilograms you are, that's a scalar. It's just a number. So then that means your weight is your force vector. That's the gravitational force on you, your weight. So here, that vector is your weight pulling you down. You'll find out as we go along that your weight is your mass times the gravitational constant. The gravitational constant, that G is always going to throughout the whole semester, it's always going to have the same number. That'll be so first off, we're kind of jumping ahead here, but I want to see if you can actually suss this out. Is gravity a position, a velocity, or an acceleration? It's an acceleration. So it's going to have units of meters per second squared. You're going to start to notice some of these units are very common for certain things. So like acceleration, meters per second squared. So this gravitational constant you're going to use over and over and over again is going to be about 9.80 meters per second squared. Now, vectors can go in multiple dimensions. So let's talk about, let's just give a little short blurb about projectile motion. I know you throw something, it goes in an arc. Now, I am going to show you, we are going to talk about the fact that we can have three-dimensional vectors, but at this level of physics, we usually just stick to 2 dimensions. Three-dimensional vectors, you really just add one more component and all of the processes stay the same. So let's just have a little coordinate system here. So that direction will be positive y. That direction will be positive x. And let's say you throw an object. And it's going to go in an arcing motion until it hits the ground on the other side. Now we are going to analyze systems like this as the semester goes on. But at each point here, you could have a velocity vector. Say here. You have velocity vector 1. At the peak of the flight, velocity vector 2. As it's coming back down, velocity vector 3. So you can analyze each specific moment of the flight with its own vector. And so as you can see, you're going to, now this is where you're going to have, when you do this, where you're going to get used to how these vectors change their components. So if you notice vector 1, it points up into, and we're going to be talking about this. If this was on a 2-dimensional set of axes, that's going to be pointing up into what we know as the first quadrant. Okay, well, that means both your x and y components are positive. Your vector 3 is pointing down into what would be the fourth quadrant. So which one of the components becomes negative in the fourth quadrant? Y. The y component is then going to have to be negative. Just to see if anyone's catching on, look at vector 2. If you were doing this mathematically and you had to add in vector 2, you should automatically see one of the components becomes 0. Which one is it? Y. So all of your velocity is an x. So we love this when this happens because this, when we're setting up equations, this allows us to start canceling a lot of stuff out. So if you're trying to find like, oh, what's the maximum height? Of the flight? Okay, well, I need to know the maximum height is where y equals 0. So you start using stuff like that to figure out your problems. And then of course, who's seen that unit before, the Newton? Okay, that's going to be your force. That's going to be your unit of force. And so as we're going through some calculations, you may have to break it down into its basic SI units. So the Newton is going to be the kilogram meter per second squared. So you see, again, that makes sense with mass times gravity. Gravity is meters per second squared. It's an acceleration. And then of course, mass is in kilograms. So you have a mass times an acceleration. And that's going to be your force unit, which gets us back to Newton's second law. Okay. graphical vector addition. We're gonna get through this pretty fast because you need to see what it looks like, what geometrically when you add and subtract vectors, but this is not how you're gonna be solving your systems. When we get to the part where we're talking about vector components, that's where you really need to focus in and practice that. Vector components are what we're going to use to calculate pretty much everything. Okay, so when we're adding vectors, we're always looking for what's called a resultant. A resultant vector is the addition of all the vectors in the system. A lot of what you're going to see in this first semester, the textbook uses net force. Sometimes I'll change that to total force, same thing. So it's like if you're trying to find the total force on a system, that's going to be your resultant force vector. So let's say I have vector A, and I'm going to add to it vector B. So what I'm going to do then is I'm going to put the tail of B at the head of A, because then the addition is represented by the resultant vector going from the tail of the first vector to the head of the last vector. And what you get here is your resultant vector A plus vector B. Now you notice how I said from the tail of the first vector to the head of the last vector. Notice I didn't say the first and the second. Why do you think I said the last vector instead of the second? I can have as many vectors as I want. I just start lining them up, tail to head, tail to head, tail to head. At the end, I go from the tail of the first vector to the head of the last vector. I could have 20 vectors in there. So, for example, let's say we had, can't make all these different colors. We don't have enough. You could do A. C. We will put one more in here. E. I'll use that for this example, but you'll rarely see me actually use vector E because next semester you're going to have a lot of this, and that usually denotes electric field. But for this example, we're just doing alphabetical order. So then your resultant, of course, would be from the tail of the first vector to the head of the final vector. Well, your resultant in this case so again, and you could continue this on. So one of the ways that you use vectors like this is like, let's say you're analyzing, total displacement on a map. So, like if you were trying to figure out, like you went all kinds of different places during the day, and you said, well, what's my total displacement? Is that the same as or different than your total distance? Different. So your distance is the magnitude of each vector all added, all of them added together. Your displacement is the vector addition. And it's going to be, so then you would say like your starting point is right there. Your total displacement is going to be the magnitude of that resultant, not the total distance you traveled. So, I mean, if you ever wanted to get fired, there's a fun joke you can play. In physics, if you start, like when you got up this morning, let's say you started calculating your day as soon as you stepped out of bed. If you end your day at exactly that same spot, and according to physics, you did absolutely no work today. And so if your vector addition adds to 0, you'll find out that work is 0. So if your boss goes, you didn't even do any work today. If you look down and you're standing at the exact same place you started your day, and you can go, hey, you're right. They don't typically like that, but it's funny. Okay. Okay, so again, I said directionality is going to become important. So one of the things you're going to have to keep track of is what's called your coordinate system. The system that you're solving your problem in. This right here is a typical Cartesian coordinate system. You've all seen this before. Some textbooks you'll see it called a rectangular coordinate system. Cartesian, rectangular, same thing. And so this is our typical, we have the XY axis and we have all of our quadrants, 1, 2, 3, and 4. We have to keep track of what quadrant we're in. Because when we're solving for components, we may only have an angle from, I don't know, let's say we have an angle from the negative x-axis up into the second quadrant. Well, anytime you use sine or cosine with an acute angle, you're going to get a positive number. But as you notice, both of the coordinates in that quadrant are not positive. So in quadrant 2, you say, oh, I'm in quadrant 2, x has to be negative, y has to be positive. You're going to have to start keeping track of that stuff. I will show you how to calculate from multiple different angles. You'll see that you can either use the sine and cosine to figure out your components, or you can use the generalized component equations and measure everything from the positive x-axis. So we will end up solving for a vector in each quadrant, just so you can kind of see how that works out. We'll use different angles in the quadrants to figure it out. Because your sine and cosine are really based on where your x and y components are. It'll make sense, trust me. Now, and this is where you're going to go, oh, thank God. The two coordinate systems that you use a lot and say, you know, what I do, like quantum mechanics or even electrodynamics, but we're still going to use Cartesian, electricity and magnetism, are cylindrical and spherical coordinate systems. So imagine you're flying through space. Spherical coordinate systems are what you would use. What do pilots call it? Pitch, yaw, and then there's a third one. Yeah, so that's what they're talking about, is a spherical coordinate system. All of those are an angle, and once you get all those angles together, you know which way you're pointed. So for spherical coordinate systems, you would have vectors based on rho, theta, and phi. You have two rotational angles, and then rho is going to be a positional vector. In cylindrical, you'd have vectors based on r, theta, and z. So r, of course, would be pretty much like a positional vector or a radius. We'll get into positional vectors. And again, you can think of them as the radius of a circle. Now, we're not going to be using these, but these are also examples of coordinate systems. Okay, so let's talk about the negative of a vector. So negative of a vector. So let's draw one on here. Let's draw vector A. What quadrant does the negative of vector A point into? The third. Because a negative of a vector is the exact same vector, just pointing the other way. Again, those are the same length. So that would be negative A. So if you ever have a question that talks about the negative of the vector, all you need to do is flip the vector around and have it be the same length. And so this gets us, so this what this will do is get us into the geometric representation of vector subtraction. So again, you see this looks a little different. So we'll say we have vector A. Vector B. The resultant in this case is going to go from the head of the last vector to the head of the first vector. So let's just use resultant for addition. We'll just call this vector C. This is A minus B. Because well, the way we can look at vector subtraction is we have A minus B. But what also is this? This is A plus minus B. So you're adding the negative of one of the vectors. So if we start moving things around, you say, well, if I take my resultant here, I'll put it here. And then I'm going to take my vector A. It's going to go there. Because I can move these vectors around. They're still the exact same vectors. Just keep telling yourself, I'm not actually going to have to really use this. You just need to see what it looks like. And then I'm going to take my vector B, but I'm going to put it, let's see, I'm going to put it here. But then what I'm going to do is I'm going to put the arrow pointing that way, which means that I now have negative B. And from here, you can see now I have the resultant vector C going from the tail of the first vector to the head of the last vector. So what I've done now is I've reproduced an addition. So this is vector A plus a negative B. I always like to do this first because if I started with components, everyone would be upset. Once after you get through the geometric representation, you're very happy to have components. So, I don't know, let's say, what's another way we could look at this? Let me go ahead and give myself a vector A. And then I'm going to give myself vector B. This is negative B because positive B would point it this way. So then what that's going to do is that's going to put our resultant vector let's see where these meet up. Yeah, about right there. So your resultant vector C would end up there. So if you have those two vectors and you're looking at you're looking at what the resultant would be, your resultant can also fits with inside a parallelogram made by the two vectors. And so in this case, you have four A minus B. So this is just geometrically how we're going to be looking at vectors interacting with each other. We're going to, as the semester goes on, we're going to pick up more vector operations. but they're gonna be a lot clearer once we have components. So at some point, we're gonna be multiplying vectors. And when you multiply vectors, you have two ways to multiply them. There is a scalar product and a vector product. One multiplication produces a scalar, one multiplication produces another vector. And so the scalar product, if you've ever heard it before, that's called your dot product. Your vector product is called your cross product. And when we get there, you'll see why. We just use different notation to, so we know which multiplication we're using. Now, let's start getting into components. Okay, so we have a typical XY system here. Let's go ahead, we're gonna draw an A and a B on here. A, let's see. There. B. Okay. Now, when we say components, look at vectors A and B. Those vectors run in 2 dimensions. So part of those vectors are going to be X, part of it's going to be Y. Those are the components we're talking about. So you can either use solid arrows or dotted. So you could say, well, that one there. So A sub X, that is the X component of vector A. That's how much of the vector lies in the X plane, or in the X dimension. It can't be a plane because it's only a singular dimension. From here, is our Y component. Let's look at the components for B. Well, the X component runs that way. And the Y component is there. Now, to solve for these components, I made a very nifty little shape. What did I make? Right triangle. So we can solve our components using triangles, because then you know that your vectors are going to be at some angle theta. Okay, now, positive versus negative angles. This also starts to matter. Let's just say in general, positive angles are measured counterclockwise from the positive x-axis. Negative angles are measured clockwise from the positive x-axis. Now, in the case of vector A here, we have a positive theta, because if you imagine A starts out on the x-axis, then rotates up, it's rotating counterclockwise from the x-axis, it has a positive angle. This will become a little more abstract as we go along. The way I usually work with vectors is I just know what quadrant I'm in. I look at the angle in that quadrant. So like, let's say we had an angle phi right in here, that's going to be an acute angle, but you would just do the sine and cosine, you're going to get positive numbers because the angle is less than 90 degrees. But I know that so what I tell myself is I know that I'm in quadrant 2, so I know that my x component has to be negative and my y component has to be positive. But again, we're going to look at solving this in all the different quadrants. So if you were looking at this on the graph, or let's say you were solving for these, you could see that for example, your AX equals 7 units. Your AY equals 5 units. And this is why we use coordinate systems, because these components, their magnitudes, are very much going to be your XY components within that quadrant. So then your BX What is bx? Negative what? It probably is a little small to see. Negative 8. Then your by would be positive, and that's going to be a positive 4 units. So you're going to actually be getting numbers like this for the components, and we're going to be working with that. Because here's the great thing, because you just saw us add vectors geometrically. Once I have components, when I add two vectors together, let's say I added A and B, well, then I just take my two X components, add them together, my two Y components, add them together, I have my new vector. Quite a bit more straightforward. But how do we find components? Well, since we're working with right triangles, we are going to be using our sine, cosine. Tangent will come in later because sometimes you will start with the components and you're asked what's the magnitude of this vector and what's its direction. Now that's where tangent comes in. So for the most part, you're going to be using sine and cosine to figure out what the components are. So let's go ahead and, so I'm going to start using F for these. Okay, so I'm just going to kind of draw this randomly into here. I'm going to start using F because that starts getting you used to it. We're going to be using F a lot for force vectors. And then, we have an angle theta. And then we're asked, well, what are the components of this? Okay, so I know that I'm going to have an X, further, and a Y. Fx and Fy. So I started asking myself, okay, I have a right triangle. You see the right angle right there. And so then I start saying, well, look where my angle's at. So for my X component, which trig function would I be using? Cosine. I use cosine because the X component is adjacent to the angle. Does that make sense? Do you see? So that means that your Fy is opposite to the angle. So then your Fy in this case would have to be the sine. Now we're going to go, like I'll show you where the component equations come from. Once you get used to them, you can just go straight, if you're doing your homework, you can just go straight to the component equation. But I do want to see that because the angle could be placed in a number of different ways. What if I put phi as measured clockwise from the y-axis? Well, now you're going to have to use different trig functions because your x and y are going to switch adjacent and opposite. You'll get used to it. And if you don't get used to it, I will help you after I've mocked you a little bit. But so we see that x is adjacent, y is opposite. So we can say, okay, well, my cosine of theta is going to be my x component, because that's that side of the triangle, over. So let's go ahead and get some notation out of the way. I'm just going to put the magnitude of the force vector on the bottom. The two ways you might see this written. So magnitude, you either put the vector inside of your two vertical bars. So it looks like absolute value, that means magnitude. Or you could just write the F without the arrow over the top of it. So in your book, it'll be non-bolded. In your homework, if you just write the vector without the arrow, then we're going to assume that that is the magnitude. And so then you solve, you see that your X component is going to be the magnitude of your force vector times your cosine of theta. Okay, well that means I did sine of theta, my opposite, my Fy, over my hypotenuse, which is the magnitude of that force vector. And does that make sense? Because the hypotenuse, we're not worried about the direction it's going in. We just need to know how long it is. That means my Fy component is going to be F sine of theta. Now, as I said, I'm showing you this derivation from scratch. When you're doing homework, you can start right here with the component equations. You just need to make sure that your trig function is the proper one. Look at where your angle is. Don't just take for granted it's always going to be cosine for x or sine for y. Now, I do want you to make note of the fact that if we're measuring everything from the positive x-axis, this formulation for x and this formulation for y are the generalized formats. So if you have, like, let's say your vector is measured at 330 degrees from the positive x-axis. You can put that 330 into each one of these and get the proper component, because the sine and cosine will give you the proper sign. Okay, so let's just say, for example, what if I told you that the magnitude of your force vector is 9.5 newtons, and theta 57 degrees. Can someone tell me what Fx and Fy are? Now, this is where you want to make sure that your calculators are in degrees and not radians. There will be a point where we switch to radians, but for these components, you're going to want your calculator in degrees.
Just in case.
Thank you so much. New.
What do we use for Fx? Should have gotten about 5.17 newtons.
Yeah, I got five. Okay, yeah, I got 5.17. I rounded it to 5.2.
See, and that would be acceptable. So, okay, here's my rule on significant figures. I don't have the time or the desire to be a stickler for it. I had to do it when I had you guys in chemistry because it was in the textbook. And here, as long as your number is not ridiculously off, I'm not going to pay attention. But if I give you a number like 9.5 and you give me an answer of 5.1723975, that's ridiculous. Okay, keep it close. What about Fy? 7.97 newtons. Now you would be able to use these components in, for example, let's say you're finding total force. Okay, let's start looking at a vector in quadrant 2. We won't get all the way through this today, but we're going to end up calculating 3 different angles. There. So, 3 angles we're going to use there. Theta. We're going to do it again. That angle. Phi. And then the final angle. Gamma. Just measuring from 3 different places. So you can say all this vector F. So here you see Fy and Fx. But if we're using an angle phi, here you have fx and fy. And then for gamma, since it's measured from the positive x-axis, we'll be able to use a generalized format. So your x will be cosine of gamma, your y will be sine of gamma. So remember, those are your generalized formats. Okay. So I'm going to go ahead. So what we'll go ahead and put down, the magnitude of F is going to be 7.2 newtons. And gamma is 132 degrees. And so when we come back on Friday, you're going to have to tell me what theta and phi are. I'm not going to tell you.
This is gamma.
So here's a hint. If I went from X over to negative X, what angle is that? 180 degrees.
So you don't have to go on there. You can just subtract.
So you can find theta by subtracting 132 off 180. Then your theta and phi take up a 90-degree angle.
Yeah, that's what I'm.
Can you scroll up a little bit so I can see the whole number? Thank you.
So the slide, so here's the way it works. The slides I put up today, they are going to be expanded each class period as we go along till we finish a chapter and so on and so forth. So again, I suggest making notes and then transferring to the slides. You can try to keep up day by day if you want to. Also, did we talk about past sessions last time?
No.
Okay, I'm going to require one past session a week. So you have a Monday and a Wednesday session. Your past leader is Ivy Heiss. She should be talking to some of you about that. I've already talked to Mary Keithley. We made sure that our past sessions are staggered. So like hers are also on Monday and Wednesday. So one day of the week you go to hers for biochem, and the other day of the week you go to mine for physics. And then Ivy's going to be keeping track of who shows up. Because since, were they like 7 p.m.? Because each week you miss a past session, you're going to get 2 points taken off your final grade.
2 points over your overall final grade.
Yeah. I'm not, huh? No.
You're sick.
Okay.
If you're sick, then make sure, document that you're sick. Huh? No, because your first assignment won't come out till this Friday. There's really nothing for you to go over right now.
I have work.
Okay, so come into my office sometime and we'll figure out a solution. Because see, that's the thing. We can figure out solutions. But first off, I don't want everyone having an excuse. That's where I kind of draw the line. So, okay, well, everyone is going to figure out. There are some exceptions. If you're sick, you should document it. They're going to be requiring one past session a week.
Give me a No.